valuable fun time they're missing. So, who'd like to start us off with a prayer? Thank you.
And that we can to solve the problems that really Corey gives us, and that we can keep our minds open and we're sort of really safe to help us to all have a good rest of our night. And we say these things in Christ's name.
Amen. Thank you very much. You should all have your scores for your midterm now. There were 10 or so students that their exams were hidden somewhere, and we found them. There's a general authority named Lynn G. Robbins. He's a member of the presidency of the 70. He gave a talk a couple conferences ago on repentance, and he talked about a BYU professor, a physics professor, that he allowed students to take exams as many times as they wanted. He would make a new exam with similar problems, and they could take it as many times as he wanted. No, I do not do that. If I had more time, I would. It's really hard to write even a half decent exam. But I do have a repentance policy when it comes to exams. So the midterms, I will replace your lowest midterm score with your final score if your final score is higher. So you can use it to bump up one of your midterm scores. Not both, but one of them. So if you didn't like this score, then you have to do better than this test on the next test and do better on the final, and we'll move that up. Or if the next test doesn't go so well, then you can use the final to bump that up. So, but the tests do get harder. So we're dealing with much harder material now than the first stuff. So the tests do get harder. So prepare. Okay. Reminder about devotional tomorrow. We forgot to talk about Elder Stevenson's devotional last week. I completely forgot about that. Any comments about Elder Stevenson's devotional? Two thumbs up. Okay. All right, go ahead and take some time and work on these problems, and then we'll go through them. These are kind of basic ideas in this section, kind of like, can you do this procedural kind of stuff? Then we'll talk about some ideas, and then we'll talk about a few applications if we have time. So. If you have questions, don't hesitate to raise your hand or ask your neighbor or write it on a note, pass it to a girl. Just kidding. All right. Okay, let's start going through these. So for number one, here, you can just start doing the multiplication. We're just checking to see which of these vectors are eigenvectors. And so we can start doing a multiplication. And if you multiply the matrix times the vector 2, 3, you get 7, 8. Right, so you get 4 plus that. And yeah, so you get 7, 8. And I just realized the person that wrote it up the last class did the multiplication wrong. That's why it threw me off. I'm like, wait a second. Thanks for correcting it, Alec. So, is 2, 3 an eigenvector of this matrix? So no, because 7, 8 is not a scaled version of 2, 3. Can I multiply 2, 3 by a scalar and get 7, 8? No. So there's no S where you can do that. So can't do it. So 2, 3 is not an eigenvector. If you multiply this matrix times 1, 1, you get 3, 3. So is 1, 1 an eigenvector? Yes, because the effect that this matrix had on this vector was the same effect as just multiplying that vector times a scalar. Okay, so it's one way of thinking about an eigenvector is an eigenvector for that matrix is multiplication by that matrix has the same effect as just multiplying that vector times a scalar. And so that's what we have here. X is an eigenvector if the matrix times the vector equals lambda. That Greek letter is lambda. It's the Greek letter L. And so 1 gets scaled by 3. So lambda equals 3. So the eigenvalue, this is question number 2. What is the eigenvalue associated with the eigenvector in 1? It's 3. So the eigenvalue is 3. And these go together. Like this eigenvalue corresponds to this eigenvector. Sometimes the eigenvalue might have more than one vector. In this case, it just had 1. Okay. Yeah. So this is the eigenvalue. This is the eigenvalue for that eigenvector. Okay. Questions about 1 or 2? Yes. Would it not have all the scalar multiples of that vector? So the question is, would it not have all the scalar multiples as of this also as an eigenvector? Yes. So number 4 says, well, what happens if you double it or triple this or multiply it by some number k? Well, it still has the same effect. I can multiply 2, 1 and 1, 2 times like 5, 5. Which is just 5 times 1, 1, and I get 15, 15. Okay, so it's also an eigenvector, but we'll just group all of the eigenvectors that are scalar multiples of this with this one. So we know that hey, this will capture all of the eigenvectors that lie on that line, and then we'll look for another one. So okay, yes. Yes, it's possible. It's that question for those that are online. Is it possible to have a completely different line associated with that same eigenvalue? Yeah, then you actually get a plane. So it's possible to have a matrix where you have, like let's say you're in R3 and you have an eigenvalue that comes up in the null space, and the basis for the null space is two-dimensional. Then actually any vector in that plane will be an eigenvector. But we'll get to that in the future. So hold off on that. We're just trying to work with the basics right now. So okay, other basic questions. No, those are great questions. So we'll get to that one. So Ben, is it Ben? Did you have? I thought you were raising your hand before. But, okay. All right. How about number 3? Okay. So before I dive into number 3, I want to talk about a few things. Like, why are we taking the determinant of that particular thing? So this all starts back to the definition of an eigenvector and the eigenvalue. We're looking for the vectors where the multiplication of the matrix times that vector is the same as scaling that vector. Okay, and then we do a little algebra. You can take ax minus lambda x equals 0. So the 0 vector. This will produce a vector. This will produce a vector. So I get out a vector. Then I can factor out. I'm going to factor out the x vector. But I have to be careful here because this is a vector. This is a scalar. I'm sorry, this is a matrix, this is a scalar. It doesn't make sense to subtract off a scalar from a matrix, it's not defined. So what I really meant was this. So I take the right sized identity matrix and I take the matrix minus lambda times the identity matrix. Okay, that's what I mean there. And now I have the situation where I have a matrix, I multiply by a vector and I get out the 0 vector. We really only care about vectors, about eigenvectors that are not 0. Okay, not the 0 vector. So eigenvectors have to be non-zero vectors. So I have this situation where I'm multiplying by a matrix. I have a matrix times a non-zero vector, and I get out the 0 vector. So what does that mean about this matrix? Okay, null space has a free variable. Nice. Yeah. Or what are other, there's probably 25 different things we could say about this matrix that are equivalent to that. So that's really nice. What? Okay, its columns are not linearly independent. Its determinant is going to be 0. It's non-invertible, like all of those things, right? So, so this is a non-invertible matrix. And one of the things we know about non-invertible matrices is the determinant is 0. So we use that one, we go that way, because that gives us a way to get an equation to start solving for lambda. Okay. So, so Danny, that answered your other question, right? So you start doing the algebra here. You get to this point, you have to do a little thinking here to realize, hey, this means that this has to be non-invertible because we really only care about x's vectors here that are non-zero, and so this is non-invertible. Hey, I know the determinant of a non-invertible matrix has to equal 0. So now we start finding those determinants. So this is the key in finding the eigenvalues. So we set up a minus lambda I and start finding this. You do this equation. The really hard part here is realizing that a minus 1 times a minus 3 equals 3. Right, Seth? Yeah. Okay, just making sure. All right. So yeah, you factor down that you factor down, you solve, and you get lambda equals 1 and 3. So these are the eigenvalues. Okay, those are the eigenvalues associated with this matrix. Okay, questions so far on this? Just finding the eigenvalues? Yes. Oh, great question. So the question is it only for 2 by 2 matrices that the determinant equals 0? No, but we haven't yet learned how to take determinants of larger matrices. That's actually the next section. So we'll spend a couple days on 4.2, which is all about understanding determinants, and we'll learn how to take the determinants of larger matrices. So, but it is true for any square matrix of any size. So nice. Okay, any other questions about this process so far? Okay, so now how do we use these eigenvalues to find the eigenvectors? Well, we go back to this matrix, and we actually will subtract off each of our eigenvalues. Where are they? 1 and 3. So let's subtract off 1 first. So 2 minus 1 is 1. I'm just going to write it out here. Yeah, so 2 minus 1 is 1. I get 1, 1, and 2 minus 1 is 1. So I get this matrix. Is this non-invertible? Yeah, it better be, because otherwise you found the wrong eigenvalue. So, yep. And then the key is, what's the null space of this matrix? The null space here, a basis vector for the null space, or basis vectors for the null space, are your eigenvectors. So, so what vectors make this true? Well, it turns out we've translated the problem into a null space problem. So what is the null space of that matrix? And then you row reduce. We do what we have already done a lot here. Row reduce, you've got a free variable. You better have a free variable in these, at least one. And then you solve and you find the basis vector for the null space. So minus 1 and 1. So this is an eigenvector. And it's the eigenvector associated with 1 as the eigenvalue. Okay, so this and this 1 go together, okay, kind of a pair. Now we do the same thing with 3. We had another eigenvalue. So, so we subtract off 3, we get, in this case, you get a minus 1, 1, 1, a minus 1. And so you subtract off 3, you row reduce, you get this, and then you find the solutions. There's infinitely many. It's a line, and the excuse me. This is a vector on that line, so the span of that gets the whole line. So that's a span of, and that's a basis vector for the null space. Okay, so now this is, so for lambda equals 3, we get this eigenvector. So these go together. So each eigenvalue will have at least one eigenvector. It's not always eigenvalue, eigenvector, eigenvalue, eigenvector. It might be an eigenvalue and you might have 2 or 3 or 10, who knows. Okay. Any questions with this part? Seth, you can ask your question. I won't make fun of you again.
Just in general, I mean, for the purpose of this eigenvalue eigenvector is that we take a transformation and we show that, like, for some given vector, the whole transformation just turns into a scalar.
Yeah, for some vectors, like which vectors are the ones where that transformation just scales them? Yeah, or is the same as scaling? But is your question like, why do we even care about that?
I guess, I don't know, I'm just finding it hard to picture that in my mind. Like if we take like a flip over the axis, I don't see that as scaling.
Okay. You're my plant here. Okay, so I've got a few transformations here. One is reflect over across the line y equals x, so it's not over an axis, but it's reflecting across the line y equals x. A kind of scaling where we double in the y, triple in the x, and we rotate by 90 degrees. Here's 3 transformations. We could write down the matrix that each of these would do. You can do that if you want, if that helps you here. But the task here is to just think about the transformation and see if you can find out where the eigenvectors are for each of these. Okay, we're just dealing with the plane, so there's at most 2 eigenvectors, at least 2 real eigenvectors. So, okay, so so Seth said he had a hard time thinking about like the reflection. Now everyone gets a chance to think about it and see if they can find vectors that one way to think about it is, can you find a vector that stays on its span? So it has to stay on the line that's spanned by the original vector. So, okay, take a minute and work on those and see what you can come up with. All right. Okay, we're running out of time. Okay. What did we think about this reflection one? Were we able to find anything? So here's the line y equals x. So we're reflecting this way. We could actually write down the matrix 0, 1, 1, 0. This swaps your y's and your x's. So the question is, can we, just thinking about the transformation, can you find a vector and the transform vector that lie on the same line? So did someone find any of these? Seth, a chance for redemption here, because you said you had a hard time thinking about one. Did you find one?
Just anything orthogonal to that line, so like I'm thinking like -1 and 1.
Oh, so anything orthogonal to that line, so -1 and 1. Okay.
And then like the eigenvalue would be 1 because it can't like scale.
So the eigenvalue, it's not quite 1, but hold it. It's not 0. Hold on a second. So let's make sure we understand. So Seth said a -1 and 1. Okay. Some of you may have said 1 and -1. Either way, that's okay. And so why did you say this was an eigenvector? Okay. So you imagine it flipping over, you reflect it, and they lie on the same line, right? That's the property of the reflection, okay? So this should be an eigenvector. Any vector from the origin that lies on that line will be an eigenvector. So what's the eigenvalue associated with this eigenvector? So Seth's first impression was 1. It doesn't change in length, but there's one thing it does change. -1. So the eigenvalue is a -1 for that particular eigenvector. Okay. All right. Is there another one here? Were you guys able to find another one? Yes. The vector 1, 1. Yeah, anything on this line. So 2, 2, pi, pi, -7, -7. Any of those, they will not change. Well, yeah, they just stay there, right? So what would the eigenvalue be for these? It would just be 1. Eigenvalue of 1. Okay. So we found 2 eigenvectors in this case. We're in R2. You will at most have n eigenvectors in Rn. So there will be at most 2. Unless it's the identity matrix you're dealing with, and then every vector is the identity. Every vector is an eigenvector. But yes. Yeah, so that question was, why is a -1, 1 and 1 a -1? Why could we both consider them, why could we take either of those to talk about that is the eigenvector? And that's because they lie on the same line. And I can get, so any vector on that, the span of any one of those is going to define a line. And I actually know any vector on that line is going to be an eigenvector that will be scaled by a -1. If I multiplied it by that matrix, it's going to be a -1 of what it started out to be. No worries. Good question. Okay, other questions? Yes. You mean like the eigenvectors? Do they have to start here? It's easiest for me, and you'll be fine in this class if you just always start with, if you're thinking about eigenvectors, if you're just thinking about them as starting from the origin. What was our other transformation? Oh, scale. We scaled 2 in one direction, 3 in another direction. So we scaled 3 in this direction, 2 in this direction. So anyone find some eigenvalues here, eigenvectors? Yes. 1, 0. Okay. Why did you say that 1, 0 was an eigenvalue? Okay, if you pick this one, you can think about this stretching this way, and if you pick something on that axis, it just gets stretched. So nice. Okay, so times 3, great. So that was 1, 0. and it goes to 3, 0. Okay, what about another one? Anyone? Ben? 0, 1. Yep, so 0, 1. And great question. So what about 3, 2? Like, can you pick anything here? So these are the standard basis vectors. Okay, let's do -3, -2, just because it gives me some space here. So what about -3, -2? So what about this vector here? -3, -2. So if I stretch it 3 in this direction and 2 in this direction, I get a -9, -4. Is that right? Yeah. Is this a scaled version of this? It's not, right? Yeah, it's not. So if I'd go 3 in this direction, 2 in this direction, I get something like that. So it doesn't stay on that same line. So good thought. Rotation. There are no real eigenvectors. There's some complex ones, but there's no real eigenvectors with the rotation of 90 degrees, because every vector gets taken off. Every new vector can't end up on the line it started off. So these are really important. Next to the idea of matrix multiplication itself, eigenvalues and eigenvectors are the most important thing in linear algebra. They're the most important thing to understand about a matrix. They tell you all sorts of things, and they have a bazillion and one applications. Here's one kind of cool thing. Oops. Okay, so this is a simple linear population model where we have rabbits and foxes. The foxes eat the rabbits, and the more rabbits there are, so that the foxes grow faster. This is a pretty simple population model. I can change the number of rabbits. Okay. Oh, so here's this red one is the first year, and then you can see, like, in about 6 years, I end up over here. What's the problem? What does this model predict if I start right there? I get negative rabbits. All the rabbits will die off. Okay, so the foxes eat all the rabbits. I can move them over here. I don't know what happened. Did you kick me? Okay. All right, we're back. So you move it over here. This means the rabbits and the foxes both tend to grow. Yeah, I don't think you're hitting anything. Am I kicking something? Maybe I should step back. Okay. But look at what happens. Look at that spot. What happens there? Someone tell me what's happening to the population here. Yes? They increase perfectly together in harmony. If the fox is eating the rabbits in harmony, they all sit down together. Yeah, no, what you're saying, like, the proportion stays the same, right? Like, there's just this kind of perfect balance between the foxes and the rabbits that the populations just grow proportionally every year. This might be in some ways an ideal situation, but if I even move just a little bit in the wrong way, the rabbits die off. In this model, the other way, everyone's happy. There's just the rabbits and the foxes just grow. It's just that the rabbits get to be, they grow a lot faster than the foxes do. Well, this line right here, that line is an eigenvalue, an eigenvector is spanned by an eigenvector of this matrix right there. So it tells me something really important about this system. The other eigenvector is actually down here at 0 and 1, like if you only had rabbits, the rabbits just grow. So if you didn't have foxes. So and knowing the eigenvectors, it splits up the system, and you can understand, hey, if I'm in this, if I'm above that line or to the left of that line, the foxes are going to die, the rabbits are going to die off. But if I'm to the right, something else is going to happen. That's just one quick application. Here's another one. I won't go into the details. You don't have to understand all the details, but because there's a bazillion applications. But this is called principal components. Those of you that go into statistics and a lot of social sciences, if you go very deep, you'll learn about principal component analysis. And it's a way of doing data reduction and trying to find patterns in your data, meaningful variation in your data. This is a two-dimensional example and a three-dimensional example. The direction of the largest variation is that long arrow right there. And that's probably the most important dimension that you care about. And you want to find out what dimension that is, and it turns out to be an eigenvector associated with the largest eigenvalue of your correlation matrix. So yeah, those are all eigenvectors somewhere. So I did principal components with the survey that you guys took the first week of class. Remember, you guys took a preference survey with 9 questions. So it looked like this. So one thing that principal components can do is it can reduce the number of dimensions. Like I asked you 9 questions, but it turns out there's really only 3 dimensions here. There's not really 9. I get almost all the data from 3 dimensions and not a 9-dimensional space. And so I put it into the factor analysis. So it finds the correlation matrix, and then it looks for the eigenvectors, and it picks the 3 largest picks the vectors with the 3 largest eigenvector values. And these are the eigenvectors, and you look for large values. So I've highlighted the largest value of each of those things. I have it in a better, more interpretable way down here. So, okay, so these were the 3 factors. The most important factor was that first one. So if you've picked night owl, your last minute person, you liked summer, and you liked friend groups over 1 versus 1. If you tended to pick one of those, or if you were high on one of those, you tended to be high on the other ones. And if you were morning glory, early prep, or winter one-on-one, if you tended to be click one of those, high on one of those, you tended to be high on the other one of those. Okay, so we might call this like the fun dimension, or the party dimension, or the study dimension if you want to focus on the other end. Okay. Then there's some other ones here. This is the second one. ESPN, sweats and hoodies, and camping went together. Netflix, dress up and resort went together. I think there might be a gender, yeah, there might be some gender effects going on there. Might be associated with gender. And then video games and fixing a car, and board games, writing a poem song. There also might be a gender thing there, but I didn't put in gender into the model. But what I did do is I looked at these. I used these to figure out, for those of you that actually put down your real names, I matched up your score on each of these scales and your midterm score. And the people that were higher on this end of the first spectrum did significantly better on the first midterm. Just saying. All right, have a good night. I mean, go to bed early. That's what I meant. So.